Again, I'd also like to thank the Council of Tall Buildings for choosing one of our projects for the innovation shortlist. And let's see now. Oh, okay, let's jump straight in. My name is Williamson-Taylor. I'm one of the founding directors of AKTII, AKTII. We're structural engineers based in London. And this building I'm going to talk about has been put in the Innovation Award for the whole building. And it's all to do with the approach and the results. We were asked about almost 10 years ago to whether we'd like to get involved in a very challenging concept by a client who was trying to partly solve some of the affordable housing in London. And the brief we were given was to try and find a way to provide accommodation on a very tight site. And the solution for this was you have to go up. You got to put a tower. I mean, on this slide shows some of the issues we had to deal with: supply chain, financing program, the usual problems we normally have with any kind of building, but especially tall buildings. Now, London, the roads in London are very narrow. Trying to get things around is difficult. But also, there's also the issue of trying to make a reasonable cost for a tall building, which is not going to be sold to the rich in London. So, how do you deal with that? The usual approach in terms of modular, which is very popular, to try and reduce installation cost, was when we went through those. Our approach was to say, well, rather than create something new where you're going to have a risk of actually installation, was to actually take the existing known materials, which we know the contractors and the fabricators are comfortable with, and actually push it and actually stretch how we can use them much more than is usual. This requires pushing the codes and taking some risks. Now, as engineers, for some reason, we seem to stop taking risks, and we seem to stop pushing the boundaries. I mean, the Council of Tall Buildings is fantastic because there's a number of engineers here who are pushing the boundaries. So the issue, what we then did, was to actually work very closely with the architect to start with, who were actually quite open to the fact that we're going to try and design this building literally collaboratively. So the whole form was actually developed not just from the architect and the engineers engineering it, but actually really working together. Now, the whole process, as we know, of collaboration is always a tortuous one, and it's always seen as being very negative, which we don't believe is the case. It can be seen as being positive, and we work with Ivan Haber, Roger Stark Haber, on the project. Now, this is the area of London where the site is. It's South London. In Southwark, if anybody knows the area, Elephant and Castle. It's in the Elephant and Castle. A number of tall buildings there. And this is the building. The tall building is 157 meters tall. Sorry, I can't convert in feet right now. It's 157. The dimension of the base is 25 meters by 25 meters. So you can do the maths. I'm sure the structural engineers can do the maths. It's got the tiniest core ever. The core is literally just under 10 meters by 10 meter core. So for us was to actually look at every single component material of how this building works. And rather than actually having each material doing What we as engineers expected to do was to push the boundaries beyond that, to do more than that. There's no dampers in this building. Sorry. That was one of the challenges we gave to ourselves. So to start off with, we worked very closely with the architect to actually understand their drivers, because at the end of the day, yes, it's an affordable housing, but it still had to have very high value. A number of options were done in terms of looking at the tall building, and there's a podium building which was done in timber, and that's for another day, an 8-story podium. So a lot of options were done in terms of how we sit this tower on the site and what it meant. How do we create value at very low cost? What is considered low cost in London? So the views were important, the base dimensions were very important, and actually creating a space with external balconies for every single flat was important. So one of the drivers was the fact that we had to have 8 flats per floor. Now, a bit of 101 basic engineering on towers. The core is where you start off with. The core is there to deal with the stability. But as I said before, the cores are just under 10 meters by 10 meters. So if you do the maths, it doesn't work. Outriggers, provide outriggers and use the external columns. Yes, but we're talking about low cost here. It's another expense you got to deal with in terms of the structure. So we did what's on the right. What we decided was to actually look at every single floor. Keep an eye on the time. This is the layout of the typical floor. We actually broke the core. The core is not torsionally rigid. And that is where the conversation and the dialogue between the architect in terms of creating valuable space, proper space, came into play. So rather than having a completely steel core, we didn't. We actually broke it up to make sure the function of the flats and the floors work as efficiently as possible. The second thing we decided was we were not going to post-tension the slabs, because from experience, post-tension at high level, yes, we all do it on other towers and stuff, but there's actually an installation cost to it. And those costs and the coordination actually either makes the whole process a bit more complex, or it actually provides a lot more coordination to the facade and make the facade more expensive. So no post-tensioning. The dimensions are roughly about just over 8 meters, the big span dimensions. The second thing we spent a lot of time looking at was to actually spend a lot of time with the contractors, the trade contractors, the guys who are going to install it, to understand issues of craneage, what they can lift, and how that can be done. So we came to the conclusion that the facade and the structure has to be combined as an envelope rather than separated. And they were all going to be precast walls. So all the blue areas are all precast walls. And the green are also precast twin wall system. I'm sure the engineers in here will know what I mean by twin wall system. That allowed us to actually install reinforcement where we need it within the core of the twin wall system, which are the 4 green elements shown on the slide. The core was jump formed, wall thickness 500 on the lower section, 300 on the top. The walls are roughly 300 to 200. So these are the blue elements, which are precast concrete, and the green elements, which are twin wall system, which we used. There's a lot of conversation in terms of the combination of how the space can be used and how flexible, how we can make it as flexible as possible. And you can see in terms of the economical situation, the time in London, you can see from 2008 to 2014, when it started on site, how the usage have changed, but it was still affordable and low cost. This is the structures coming up. Now, one of the things we did, if I just go back for a bit, one of the approach we did was we used every single floor on this tower as an outrigger. Now, in structural engineering, in engineering, you tend to do your analysis, you end up where the forces are, you then design the outrigger to transfer those forces. We didn't do that. What we did was, having spoken to the trade contractors, we determined how they were going to fix the reinforcement between the core and each slab using a straight bar. Then we calculated the maximum moment or the maximum force that connection can take, and then we fed that into the analysis and see how the results of that, and then how we transfer the forces, the stability forces between the core and the perimeter concrete walls. So moving on, this is the foundations. Very simple piled raft foundation was used, the solid reinforcement going in. And this gives you an idea of the settlement we had between the core and the rest of the floor plate. This is going up. So you can see the stitching of the precast slabs, precast walls on the perimeter. And this is the tower going up. So as a ratio of the perimeter to the height of the building is very similar to some of the tall towers in Chicago, New York, London, everywhere else, but just a tiny tower. So in terms of components, you can see the twin wall system that was used for the walls and the precast system on the other wall. Now, just a little bit of quick analysis. We actually analyzed the implication of not just the stress, because the walls were acting as, in terms of taking horizontal forces, stability forces, the floors were doing the same on almost a floor-by-floor basis to make sure they were working very hard. Now, this is a very interesting slide, because having done the analysis, we were able to determine what proportion of stability goes into the core, into the cross walls, and into the external walls. And as you can see there, some of those percentages are there. I think it's about 65% on the core and the rest on the perimeter wall. Now, in terms of frequency, we calculated the frequency, the stiffness of the building, meet the code requirement, not a problem. And we also did, we actually used CFD analysis in terms of the wind forces as we were doing the analysis to make sure we are within acceptable limits. The balconies were all built to be bolted on and self-supporting, and then cables or rods were then used to deal with the vibration issues to the top of the tower. How am I doing for time? This is the wind analysis we used. Now, also, because it was cost was an issue, every single component, the number of components in the building was limited. Rather than being, the concrete had to be fair-faced, good quality, that can just be painted. The ceiling, we were not using any plasterboard or finishes, so literally painted to bring it within cost. So these are some of the information. And now this is also another important slide, because at the end of the day, we had to make sure that the slab, because each slab was acting as an outrigger, the forces between we had to make sure the cantilever forces were at their limit for it to actually work as an outrigger, for each slab to work as an outrigger and transfer the stability forces to the external. Now, yeah, I got 3 minutes. To finish, having done all the analysis, we also had to do a follow-up. So with Bristol University and the office, we actually installed some accelerometers on the building to actually then do a back calculation to see in terms of reality, to see whether our analysis and the fact that we're pushing this building in terms of each of the elements to its limit actually worked. So we had a team, and we're actually working with RWDI as well on this. And we had some accelerometer installed with the university and our staff to measure, and for the past 6 months we've been measuring not just the wind, but we're also measuring the acceleration and also to see how the building is performing. The early results are actually showing us, this is where all the locations where we actually installed the accelerometers. This is just a view. These are the components, all glued to the concrete. The results are actually showing that the building is over 20 times stiffer than what we calculated. Now that says something about what we as engineers, what we do. Every single building we do is a new building. There's not enough research in terms of what we do, and there's not enough innovation. So it's given us early readings that show that we're over 20 times stiffer. The building is actually stiffer than what we calculated. So it can actually be a lot more flexible, and we can actually push it even more. We're going to be looking at the results real time for a whole 12 months, and then there'll be some more information presented to the public in terms of how this building is performing. And we've been asked to look at a number of other buildings as well. And also, obviously, also making sure we understand how the wind is performing throughout the year. So these are the guys doing the real work. And I think these are some of the results we're getting, as you can see. In terms of the velocity, the wind velocities, we're getting some information as well on the acceleration, and also some the response to acceleration in X, Y, and Z direction. Finally, this is our goal. This is what we're trying to do. We're also working. We also have a CFD analysis, which we've wind analysis for comfort, which we've developed in-house. And our long-term goal is to try and make sure we push the use of towers as far as we can before we start putting dampers on them. Thank you.